We're going to move into section 3.3 today, rates of change and behaviors of graph. So rate of change is maybe not a term that a lot of people heard in this course. By definition, it's if we have a given function f of x and we have the interval that it's on, usually it's an x interval from a to b, or it could be from like 2 to 5, for example. We find the average rate of change by plugging in b to our function, subtracting it from if we plugged in a into our function and took that result, and then all over b minus a. Now, we call it average rate of change more often than not when we're talking about applied word problems, stuff like that. But actually what this is more commonly known as is slope. It's just a really weird way to kind of look at the slope formula, but for those who know the slope formula, typically we go rise over run, or if you're feeling particularly fancy, y2 minus y1 over x2 minus x1. Well, at top, that's y2, f of b is y2, f of a is y1, and then the bottom is just your change in x. So that's really what average rate of change is its slope. So to see that in practice when we're dealing with a function like this, I want to find the average rate of change of f of x from -2 to 5. Well, I would plug in -2, I would plug in 5, and I would get that result. So I kind of did that all at once, but to break it down on the fraction, the top left of the fraction is if I plugged in 5 into my function, there's a 5 now in the denominator. The very top right of my really big fraction is if I plugged in -2 into my function, and then the bottom of my average rate of change is just my 5 minus a -2. So then there you kind of just have to simplify all the way through. Ideally, you're going to be left with just a single fraction or maybe even a whole number. So 5 plus 3 gets me 8, -2 plus 3 gets me 3, and so the top becomes 3/8 minus 3 over 1, all over 7, 5 minus -2. If I subtract the fractions on top after getting a common denominator, I get -21 over 8. And then if I'm dividing my fractions, that 7 becomes 1 over 7, multiply straight across. That's equal to -21 over 56. And not to kind of get lost in the noise of all of that, because there was a lot of fractions, but all I really did was find my f of b, find my f of a, plugged it into my average rate of change formula, and then simplified. It's just, unfortunately, with this example, the simplification was a little bit tricky because I had to subtract fractions and then divide fractions and multiply fractions. But that's the idea. And then, as always in this course, if you have a fraction and you can reduce it, reduce it. So that's exactly what I did in that final step. So to see it again, here we have a function f of x is equal to 2x squared plus x plus 3, and now I have a little bit weird of an interval, 0 to c, but that's perfectly fine. Quite often when we're dealing with average rate of change, we don't have a nice number, whole number, or even a nice fraction with numbers in it. Sometimes we have variables. But I'm still going to use that average rate of change formula that we saw in the last slide. I'm going to plug in c into that function. I'm going to plug in 0 in my function. I'm going to subtract those on the top of my fraction, and then I'm going to subtract my interval on the bottom of the fraction, so c minus 0. And now I kind of more explicitly did it in individual steps for this problem. So I found my f of c, since it's kind of weird with the squared and the variables. All I did was plug in c into my function. So I get this result, f of c is equal to 2c squared plus c plus 3. And f of 0, that's pretty easy to find. I plug in 0 everywhere there's an x in my function. I'm left with 3. 2 times 0 plus 3 is 3. So now I have all of my pieces to find my average rate of change. I have my f of c, I have my f of 0, and then I have my given interval. So I'm just going to plug those two things into my fraction. I'm going to subtract. And then I'm left with 2c squared plus c over c. Now, since both of those terms on the numerator of the fraction have a c in it, I can actually divide both parts by c, and I'm left with, well, 2c squared divided by c is 2c, and c divided by c is 1, so I'm left with 2c plus 1. Now, if one of those terms didn't have a c in it, I couldn't kind of do this nice simplification that I did all in one step, but in this case, I have c's in both terms, so I'm allowed to do that. Something worth mentioning that I guess maybe we'll see later on in the slides. If I have more than one term in my second like my f of 0 or something, it's a good idea to put a parentheses around it so that when you're subtracting, you're actually subtracting properly and you'll have to distribute the negative. Hopefully we have an example of that in the near future. Now, finding average rate of change for a graph. In this case, I actually am not given a function, I'm just given a graph, and it's actually just a bunch of points, but that's perfectly fine. We see that with a lot of examples in the real world. And I want to find the average rate of change from 1 to 4. Well, on this graph, probably should have been labeled, but if it's not labeled, we assume that's an XY graph. And so my coordinate of 1 would be just 1 to the right of the origin, and then, well, it's going to be up 2. So my value of f of 1 is equal to 2, and my value of f of 4, as I just circled, is going to be, let's see, 1, 2, 3, 4, 5 from the bottom. So using that formula, I'm going to try and find f of 4. I'm going to find f of 1. Well, I already found them. I'm going to plug them into my formula. I'm going to subtract it from my, or I'm going to divide by the interval I subtracted over. So as I mentioned, f of 4 is, counting from the bottom, 1, 2, 3, 4, 5 up. F of 1 is, counting from the bottom, 1, 2 up. Those are the 2 points. And notice I actually don't care about the other points. If I'm finding the average rate of change and I'm going for an interval, I'm looking at just the endpoints, just the value of the whatever you plug in on the left side of the interval and just the value of whatever you plug in for the right side of the interval. And so I probably should have found it, but it's pretty findable. I should subtract this and simplify it. I didn't do that on my slide for some reason. But I get 5 minus 2 is 3, 4 minus 1 is 3, and I would be left with the result of 3 divided by 3 is equal to 1. Which makes sense. If you were to draw a line connecting those 2 points that I circled, that slope would have a slope of 1. It'd be up 1 over 1, up 1 over 1, up 1 over 1, and then we would get to we would get the slope of a line that connects both of those points. So I apologize, I made a mistake. That answer should not be boxed. The correct answer for this slide is 1. Average rate of change is 1 for those 2 points. Now, we're going to talk about more of a concept or a definition here because we're moving on to behaviors of graph versus average rate of change. We talk about a graph as increasing as though, kind of imagine that you're reading a book from left to right. So I'm reading this graph from left to right. Sometimes it even helps to imagine kind of a tiny man walking along your graph. And so if we have a tiny man walking across our graph from left to right, on that red portion he is climbing up a mountain or a slope. It's not really that steep, but maybe some sort of hill. He's climbing up that hill. So we say that graph is increasing from negative infinity all the way up to 0. And 0 is going to be my bolded line. And I'm saying negative infinity because I have an arrow. So if I didn't have that kind of teensy arrow on the very left side of the graph, I would actually stop. But that arrow tells me from negative infinity all the way up to that point on 0 where that dot is, I'm increasing. And notice how I'm not talking about any of the y values. I'm not saying it's increasing from negative infinity up to 2 because we don't talk about increasing as y values. We only talk about as though we're reading a book. So we talk about the x values. So it's increasing from negative infinity to 0. We say a graph is constant if it's not changing at all. If he's not having to climb a mountain or he's not falling down a slope or anything like that. He just has a nice level playing field. And so that happens on 0 to 2 in the graph. And again, those are my x values. That's my x value interval. So it starts from that red dot and goes all the way to the empty dot on the right side. And it's kind of that blue segment. And now notice how I'm not putting brackets around any of these. That's because the graph, let's look specifically at that red dot point. Well, you could potentially argue that the graph is increasing at that point, and you could potentially argue that it's staying constant at that point. But the truth of the matter is actually neither of those things is happening. There's like a weird point or like a diagonal there that we can't actually determine what's happening. So anytime there is a stark change from either increasing to decreasing or increasing to constant, we're never going to include it. So all of that's a long-winded way of saying anytime you talk about increasing or decreasing functions, there will never be a bracket on your answer. Now for the last part, hopefully you're able to kind of piece together what it's going to be at this point. We want to talk about where our graph is decreasing. And so it's decreasing on that green segment. And we think about decreasing, again, if we want to go to kind of that tiny guy idea, is that if he's walking from left to right, he's going to start tumbling down that hill. He's going downwards. And that's going to occur all the way up to infinity because my graph is pointed or has an arrow at the end of it. So I would say my graph is decreasing from 2 to infinity. Now relative maximum and minimum. And I actually would kind of lump this last slide into this concept as well, is these, as far as an idea goes, aren't super difficult. Where it becomes tricky is we have to be careful with the definitions, and we have to be careful with how we're describing things. So usually I don't dock points from people's tests about increasing, decreasing just because they don't get the concept. It's that they're not describing the x intervals. They might describe the y intervals, or there's a couple of errors, or like here when we're going through these definitions, sometimes people mix them up or they say, how do I describe this again? So since it's so easy, don't kind of sleep on these concepts. Understand that, yes, it's not that hard to grasp what's going on. It becomes a little bit tricky when you have to explicitly write your answer or explicitly understand what the definition is. So all that's to say is going into minimums or maximums, the definition is very important. So relative maximum. Relative maximum, as far as a strict definition goes, is that the graph starts to go from an increasing graph to a decreasing graph from left to right. And if you're going into calculus at some point, we kind of talk about neighborhoods. It's not that we're talking about really what's the highest point overall in the graph. It's more we're looking at kind of hills or valleys, and what's the top point of each hill? Well, that's going to be your relative maximum. Very similar definition. Your relative minimum is that everything around that, very close to it, is going to be bigger than that point. That's not to say that it's the smallest point on the entirety of the graph, but it's the smallest point in its small neighborhood. Now, absolute maximum and absolute minimum kind of do fall into that classic definition. Absolute maximum is, I don't really care what's going on at other parts of the graphs. Maybe it squiggles up and down a lot of times. I only want to know the very, very highest point on the graph. And the same thing with minimum, I want the absolute lowest point on the graph. And something to note, relative maxes and relative minimums, I could have 1, I could have 2, I could have 50. There isn't really a set number of how many exist. Where with absolute maximums and absolute minimums, I'm only going to have 1, or possibly none. There is a scenario where I don't have an absolute max or absolute min, and we'll talk about that shortly. So with this graph, we're going to identify any relative absolute maximum or minimum. So we're going to start with, I believe, relative max. Okay, so I do have the answer in front of me, but let's talk through it. Relative maximum for this graph is a negative 216 and 212. So if you're kind of looking at the graph and kind of looking at those points, the negative 216 is the top of the hill on the left side, and the 212 is the top of the hill on the right side of the graph. And so that feels weird when we think about the term maximum or maxima. We think there can only be a highest point. Get that out of your head. When you see the word relative, you just have to think, okay, where's the top of the hill or where's the bottom of the valley, and kind of look for those in your graph. And those are both described as points. Those are not intervals. So I don't have a relative maximum on an interval from negative 2 to 16. No, I just have that point. The point negative 216 is a relative maxima, and the point 212 is a relative maxima as well. And that's going to be important. Read carefully when you're doing the WebWorks, because they might just want the y value. They might just want the 16 or the 12. So watch for that. Be careful what they're asking for. And if your answer is not working as a point, maybe just try entering in the second value. My absolute maximum is the highest point on the graph. So we have those two hills. The top of both of those hills, the biggest of the two of them, is 16. So my absolute maximum is negative 216. And notice how one of the relative maxima is the absolute maximum. That happens a lot. So don't kind of be weirded out being like, I already answered the question before. That's fine. But you're not going to have both of them. I don't want the right hill at this point because that's not the highest point. It's not the absolutely maximum point of my graph. Now moving on to relative minimum. Well, there's only one in this case. There's only one valley and it's right at 0, 0. So looking at that graph, I kind of going left to right, I have a big drop and then I shoot up around 0 and then I continue to drop off at the end. And I have an arrow at the bottom of my graph, so I can't say that's a point, so I can't talk about it as a relative minimum. Also, the point at the very, very left side of the graph, that's a dot. We don't ever talk about endpoints as relative maximum or relative minimum. So really the only thing I'm concerned about is a valley and it needs to go down and come back up. Otherwise it doesn't count as a relative minimum. Now that was a lot of explanation to talk about it, and hopefully some of you that you were able to grasp, or ideally all of it you were able to grasp, because this last explanation might take a few listens to really fully grasp, or shoot me an email if you can't fully get it. Don't feel bad. It's difficult. All that's to say, I'm prepping you for what's coming. We're talking about absolute minimum. Now let's look at the definition. Absolute minimum, the least/lowest point on the graph. Well, I'm looking at my graph, and obviously 0, 0 is not the lowest point on my graph, because when I go to the right, it gets much lower than that. So I can't have an absolute minimum of 0, 0. And the truth be told, the absolute minimum is nothing. There is no absolute minimum of this graph. And the reason behind that is when we're talking about relative minimums and relative maximums, we have to be able to give us a point. I have to say the relative minimum is 0, 0, or the absolute maximum is -216. And if there's an arrow going all the way to the bottom, there is no point. And anytime you give me a point, like let's say we play a game and you say, oh, okay, you know what I think the relative minimum is I think the graph stops at -20. So let's say 3, -20. Well, the graph keeps going down below that. So -50 is lower than that. And you know it's less than -50, -500. And we can keep playing that game all day because it keeps decreasing endlessly, so there's actually no point we can point at. So watch for that. When there's an arrow going all the way down, there won't be an absolute minimum. And on the other side of the graph, if there's an arrow going all the way up to the positive, all the way to positive infinity, there would be no absolute maximum. So you're only going to find absolute maximums or minimums if your graph stops at some point, or it has a point that is the highest, or a point that is the lowest. You're never going to have it if the arrow goes all the way in that direction. So watch for that. That's kind of a trick question. That's the end of this section.